So we are getting close to the end of Chapter 5 now, and we've built up a strategy for exploring data on a single numerical variable. When we're doing this first, for step 1, we want to plot our data and make a histogram, a dot plot, or a stem plot, or some other type of graphical representation of our data. Step 2, we look at the overall pattern, the shape, center, variability, and for striking deviations such as outliers in the distribution. For our third step, we can calculate a numerical summary to give a description of center and variability. And for any distribution, we can do this with the 5-number summary. And if we have a distribution that is symmetric and doesn't have any outliers, then we can use the mean and standard deviation to describe variability. So we've done that. We can add one more step to exploring data. We can, if we have a pattern of a large number of observations that is so regular that we can describe it by a smooth curve, then we can draw that curve superimposed on the histogram. And we'll look at doing that in this section. So first, here's an example of a smooth curve. This histogram shows student scores on a vocabulary test. And we can see that the distribution is symmetric and doesn't have any outliers. So it'd be a good data set to describe with mean and standard deviation. And it's also a good candidate for the fourth step in the strategy, which is drawing a smooth curve superimposed on the histogram. So we've got a smooth curve drawn on here, and it approximates pretty well the shape of this histogram. And if we have a symmetric bell-shaped curve like this one, this is called a normal curve. So let's talk about normal curves. So as I said, a bell-shaped curve like the one in the example is called a normal curve. When we have a normal curve, we set the total area under the curve to be 1, and then the area under the curve above any interval of values tells us what proportion of all values of the variable lie in that interval. So let me draw a picture for that. So if I have a bell-shaped curve like this one, this is a normal curve, or mostly a normal curve. My lines aren't very straight. The total area under that curve is going to be equal to 1. If I take any interval, say this interval here, and I find the area of the curve over that interval, let's say that that area is 0.1. So that area is 0.1 and my total area is 1, then that area is 10% of the total area, which means that 10% of my values fall into this range in this interval. A normal distribution has a histogram that can be described by a normal curve superimposed on the histogram. So any distribution that's got a nice shape like that is a normal distribution. And then when we have a normal distribution, we draw the normal curve over it as an approximation for the histogram. So let's take a look at an example of that. So here I've got my vocabulary scores again, and all of the bars together, all of the bars in the histogram represent 100% of the students. And we're going to treat the area under the curve as 1 or 100%. And let's look at this. So in my histogram, if I want to find a proportion of the scores in an interval, I look at an interval, say from 2 to 6 on my histogram, and I add up the areas of all the bars, and then I divide that by the total area of all the bars to give me the proportion of scores in that interval. So here, adding up the area of the bars, I get a proportion of 0.303 or 30.3%. Now I've used this normal curve to approximate the histogram. So instead of looking at the individual bars and adding them all up, I'm just going to look at the area under the curve and use that to approximate the proportion of scores in that interval. So if I do that, the area of this shaded region on the right here is 0.293, so that would be 29.3% of scores according to my normal curve fall into that interval of less than 6. So that's an approximation. These are about the same, so that's pretty good. We're only off by 1%. So that's how we can use the normal curve to approximate the histogram. And why are normal curves nice? Well, first, the center or peak of a normal curve is both the mean and the median of the distribution. And that's because normal curves are exactly symmetric. Also, the variability of a normal curve is determined completely by its standard deviation. So if we know the mean and the standard deviation of a normal curve, we can describe everything about its variability. How do we find the standard deviation of a normal curve? If you trace your finger down the graph of a normal curve from the peak, then the graph initially goes down more steeply, and then it starts to get less steep and flatten out as we get to the end of the bell. And the point at which it changes from getting more steep to less steep is the standard deviation. And then once we know the standard deviation, we can easily figure out the quartiles. The quartiles of a normal distribution are just located 2/3 of a standard deviation away from the mean. So let's look at an example. So this normal curve is an approximation of the real-life distribution of the heights of young American women. And normal curves are often good approximations for a variety of biological measures. Here, if I look at, I'm looking for the mean. The mean is the peak of my graph, so there. And that's going to be at about 64.5 inches. So my mean x bar is 64.5 inches. Now to look for the standard deviation, I run my finger, I trace down from the peak down the side of my curve, and I look for the point, which looks like it's about here. As I'm coming down, until I get to this point, it looks like I'm coming down more and more steeply. But once I get to here, it looks like I start to flatten out again. And that point is at about 67 on my graph, so my standard deviation, S, is going to be the distance from that point to the mean. So that's 67 minus 64.5 is 2.5 inches, so my standard deviation is 2.5 inches. To find my quartiles are 2/3 of a standard deviation away from the mean. So 2/3 of 2.5 is about 1.7 inches, so my quartiles are about 1.7 inches away from 64.5. So that gives me these two lines here. So my first quartile, Q1, is going to be 64.5 minus 1.7, which is 62.8 inches. And my third quartile, Q3, is going to be 64.5 plus 2/3 of the standard deviation, so plus 1.7, will be 66.2 inches is where my third quartile is here. And remember when we were making our box plots in the previous section, we said that 50% of the values fall between the quartiles. So if my area of my curve here, the total area under the curve is 1, then the total area between the two quartiles is 1/2. So that's useful. Now, why are normal distributions important? Well, they're good for several things. First, they're good models or approximations for some distributions of real data. And distributions that are often close to normal include scores on tests taken by many people, like the SAT or any standardized test. They're also good approximations to the results of many kinds of chance outcomes, such as flipping a coin many times. So if you flipped a coin a bunch of times and kept track of how many times it came up heads or tails, you get a normal distribution. So some things to know for this section. You should be able to tell if a distribution is normal and can be described by a normal curve. And given a graph of a normal curve, you should be able to find the center, the standard deviation, and the quartiles of the curve.